Hello students, in this session we are going to study the beams with moments. There is a couple or moment applied on the beam and we have to find out the shear force and bending moment diagram of the beam. So suppose let us take an example of simply supported beam. Let us take, this is a simply supported beam and simply supported beam of length L and a couple is applied, suppose clockwise, of moment M. The moment of this couple is suppose M. This couple is applied and we want to draw the shear force and bending moment diagram for this case, right? A couple is applied of the moment M. The moment of the couple is M and we have to draw the shear force and bending moment diagram. And suppose it is at the center. Suppose we are taking at the center of the beam. It is at the center of the beam, means at L by 2 distance from A and L by 2 distance from B. So how to draw the shear force and bending moment diagram of such a beam? So let us draw. First of all, we have to find out the reaction. After finding the reaction, we have to find out shear force at a cross section X and then bending moment at a cross section X. And using that equation, we will draw the shear force and bending moment diagram, right? First of all, find the reactions. Say the reaction at this point is RB and reaction at this point is RA. First of all, we have to find RA and RB. So RA and RB. Let us take moment about RA. Take moment about A. Moment of all the forces about A. And we know that sigma m about A will be equal to 0 because it is a hinge point. So the moment of RA will be 0 because it is passing through A and there is no perpendicular distance between A and RA. And moment of RB will be RB multiplied by L, and this is a moment itself, right? So it is need not to be multiplied with another thing because this is itself is a moment. So let us take this clockwise moment as positive. So you will get M, clockwise moment positive, M, minus, because it is anti-clockwise, RB multiplied by L. So minus RB multiplied by L. So this will give the value of RB, that will be equal to M by L. So this is a reaction at point B and M is known to us. M we know, whatever value is this given, and L is the length of the beam. So RB will equal to M by L, right? Similarly, we can find out RA. We know that sum of all the vertical forces should be equal to 0. Sum of all the forces, vertical forces, should be equal to 0. And there is no applied vertical force, there is only reactions. Vertical reactions are there. And RB we have found out M by L, which is positive. So this must be negative. So you can write here in this case that RA plus RB, and there is no other force in vertical direction, that should be equal to 0. So this shows that RA must be equal to minus RB or RA must be equal to minus M upon L. So this is the reaction at point A, RA. So the direction shown by us of RA is actually wrong. It is opposite to the reaction we have shown here, right? Actually RA is acting in downward direction, not in upward direction. RA is acting in downward direction basically. This is RA. Magnitude is M by L. So this is not RA. This is not RA. RA is in downward direction. We have shown here. This is in downward direction, RA. And RB is in upward direction. RB is in upward direction given by the same quantity M by L. M by L, right? So this is RA and RB. Now we can draw the shear force diagram very easily. Take a section between A and C and then between C to B, and you will get the shear force diagram, right? So take a section between here, suppose this is X section, at a distance small x, from A. So what you will get? You will get the shear force. Shear force will be, what will be a shear force? That will be the sum of all the forces, vertical forces to the left of the section. To the left of the section, this is only one force. And what is sine convention? What is sine convention? Let us remind the sine convention. I am writing here. Sine convention is, this is positive, this upward and this downward. Left upward, right downward is positive. This is shear force. This is also shear force. Left downward, right upward. This is also shear force. For bending moment, we know the sine convention. This is positive, sagging bending moment, and this is negative, hogging bending moment, right? So this is how the sine convention of shear force and bending moment were taken by us, right? So using the sine convention, this is negative basically. This is negative, m by L, it is negative because according to this, the leftward shear force in downward direction is negative. So Ra is negative for us. So find out Fx. That will be equal to minus Ra, that is m by L. Minus m by L, right? And it is valid between A and C for the time being. Later on you see that there is no effect of bending moment, no effect of couple on the shear force diagram. It will remain constant. But for the time being, let us say it is valid between A and C. Then what is Fa? Fa, that will be equal to same, because there is no x value here. This is constant, minus m by L at x is equal to 0, at x is equal to 0. And what is Fc? That is equal to again minus m by L at x is equal to L by 2, right? So this is the Fx between A and C, which is valid between A and C, right? So let us do another. So we can draw now diagram. This is our beam A, center point is C and end point is B, and this is negative m by L, and which is constant. So this is the value. Suppose this is m by L and it is constant from here to here, right? So till this value, this is our C point, right? So from here to here it is negative and it is constant, right? And this value is in magnitude m by L, isn't it? M by L constant from A to C. Now you will see that there is no effect on the shear force diagram at a point where there is a couple, right? So this can be shown by taking another section between C to B. So let us take one more section between C to B. So we can take a section here, say at a distance x1, suppose, and this cross section is capital X1, and this will be valid between C to B, right? And length of this beam we have rubbed, this is L basically, right? So now find out some of the forces to the left of this section x1. So Fx1, find out. There is only one force. There is only one force to the left of this section, and that is Ra again. And it is negative because left of the section, if it is downward, this is negative. So this is not a force, this is a couple. So Ra, there is no other force in between. So again we will get the same value, that is minus Ra or minus m by L, and again it is valid between C to B. So you can see here that both the values are same. Between A to C the value was minus m by L, between C to B again the value is minus m by L. It means there is no effect effect on shear force at a point where there is a couple. So Fc will be equal to minus m by L. According to this, there is no change, and this is x is equal to L by 2, and Fb will be equal to again minus m by L at x equal to L, right? So this is the shear force diagram. This is so we can now draw the shear force diagram. Minus m by L from C to B, and this is constant. So this is the shear force diagram for simply supported beam with a couple, right? So this is a straight line, straight horizontal line, because there is no change in shear force due to a couple. Whatever shear force is maintained at one end, it will remain constant till there is any other force, because there is no other force there in between. There is a couple, so there will be no change in shear force. So remember this thing. Now draw the bending moment diagram. Bending moment diagram. How to draw bending moment diagram? Take the moment of all the forces about x, and it will be valid between A to C. So what will be the moment at x? That will be equal to sum of all the forces to the left of the section, and there is one force only, m by L, and this is downward, and downward movement is left, that is anti-clockwise. Anti-clockwise to the left is negative, so this is negative, so it will be minus m by L multiplied by x, and this is linear variation, and this will be valid between A to C, right? And at end points between A and C, it is valid. At A, what is moment? At C, what is moment? So at A, where x is equal to 0, moment will be 0, and at C, where x is L by 2, this will be minus m by 2, right? Because x becomes L by 2. So when we put here L by 2, you will get minus m by 2, m at C, right? And this is at x is equal to L by 2. So this is the bending moment between A and C, valid between A and C, right? So 0 to minus m by 2, right? So this is a beam, this is A point, C point, this is center, C point, and this is B. Between A to C and then B, and this is negative and linear variation from 0 to minus m by 2, from 0 to linearly varying minus m by 2, right, up to this, and this distance is, this much distance is minus m by 2 or m by 2 in magnitude. In magnitude it will be minus m by 2, this much, right? So this is the bending moment diagram between A and C for the time being, right? Now what is bending moment between C and B? What is happening between C and B? So for C and B, we have taken another cross section x1 at a distance small x1 from the extreme edge A, right? So what is bending moment at x1? Sum of all the moments to the left of the section. So there is one moment of this force, m by L multiplied by x1, and this is already a moment, so there is no need to multiply something, but this is a moment, you have to add this moment also. So what you will get, this is anti-clockwise, this is negative, and this is clockwise, it is a positive, right? So you can see here, leftward anti-clockwise is negative and clockwise is positive. What you will get, the moment at x1 will be equal to minus m by L multiplied by x1 minus m by L x1. x1 is variable, and it is anti-clockwise leftward, it is clockwise rightward m. So you can write plus m, and it is valid between C to B. Then what is the moment at C and B? At C, which is at L by 2, here you can put L by 2, so you will get the moment as plus m by 2. this is minus m by 2, this is m, so you will get plus m by 2. So this is plus m by 2. This is at x is equal to L by 2. And what is moment at x is equal to L? Put x is equal to L0 at point B and you will get 0 bending moment. So at MB, this will be 0 when x is equal to L. Right? So there is abrupt change. There is abrupt change in bending moment from m by 2 to minus m by 2 to plus m by 2. You can see here at this C there is minus m by 2 and at this C there is plus m by 2. Means just at the left hand side, just to the C, if we are considering C point, just left hand side of this C, the bending moment is minus m by 2, and just at the right hand side of the C, the bending moment is plus m by 2. So there is abrupt change. There is abrupt change in bending moment from minus m by 2 to plus m by 2, like this, right? And then 0 at B it is 0 and their variation is linear. You can see here this equation mx by L, this is a linear variation. So linearly it is dropping down to 0 again. So this is the negative bending moment part of this and this is the positive bending moment part of this, right? And this is minus m by 2 and this is plus m by 2. From minus m by 2 to abrupt change at point C where there is a couple minus m by 2 to plus m by 2, right? Here and then there is a linear variation, straight line variation from C to B, right? So this is total is m, like this, there is m moment and total is again at point C there is m variation, right? So this is how we draw the shear force diagram. This is a shear force diagram and bending moment diagram. This is bending moment diagram of a simply supported beam with a couple at the center.